Hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Himanshu, he's going to talk about eigenvalues on graphs D5Q.
Yep. All right. Hello everyone. First of all, thanks to the organizers, Tina, Sabrina, and other organizers for giving me a chance to speak in this seminar. I'm going to talk about the work on eigenvalues of the graph D5Q. This is joint work with Vladislav Taranchuk, who's also at University of Delaware. The paper is on arXiv and it's under peer review. At any point, if you have any questions, please feel free to stop me or put a message in the chat box. Okay, so let's get started. So graphs are interesting objects and we want to study various properties of graphs. One of the property we want to study of the graph is how well connected is a graph, and the parameter which can measure that how well connected a graph is isoparametric constant. So what is isoparametric constant, or also called as Steger constant of a graph? It's basically minimum over all subsets of vertex set. So V gamma is vertex set of the graph, such that it's at most the half of the size of the graph of this fraction, where at the top we have number of edges going from S to S complement, and at the bottom we have number of vertices in the S. Okay, so we are looking the minimum of this quantity. So let's look at one example. So let's say this graph on 10 vertices, and if we pick S to be these red vertices, so size of S is 4, and number of edges going from S to S complement are basically 1, 2, 3, and 4. So ES's complement, size of that is going to be 4. And if we look at the ratio, is equal to 1. And for H gamma, we are going to looking at all the subsets such that its size is at most half, and we want to minimize that. So question is, can we do better for this graph? Okay, so that's what basically isoparametric constant is. Now, once we define the isoparametric constants, we are interested in the graph called expanders. So basically, it's an infinite family of k regular graphs. So k is fixed, and it's a finite graph which satisfies the following two properties. First is, if there exists a constant c which just depends on this k, such that isoparametric constant is greater than or equal to c for all n. And size of vertices should go to infinity as n goes to infinity. Okay, so these are basically expanders which we are interested in. And why do we are interested in expanders? Because these are graphs which are sparse and highly connected at the same time. Okay, so in applications, we want we desire that our graphs to be highly connected, but edges cost us whatever way it costs us. So we would like them to be sparse so that it's economically good. Okay, so that's why they are important. And there are many applications of expander graphs. They have applications in coding theory for error correcting codes. They have applications in probability theory, like for random walks. If we consider the random walk on expander, they converge pretty fast to uniform distribution, and other areas of computer science as well. I would refer to this survey paper by Huri, Linear, and Widgerson. It contains a lot of application and importance of expanders. Okay, so we talked about Steger constant, we talked about expanders. Now, expanders in general are difficult to construct because in general it is NP hard to figure out this parameter H gamma n. So we would desire to study expanders by other means. And that's where spectral graph theory helps us. So this is very basic definition. So given a graph, adjacency matrix of a graph is n cross n matrix, whose edges and whose rows and columns are indexed by vertices. And xyth entry is basically number of edges between x and y. And this is a symmetric matrix, so all of its eigenvalues are real and they exist. For example, for Peterson graph, they are 3, 1, and -2 with respective multiplicities. Okay, and this fact has been known that for a connected k-regular graph on g vertices, largest eigenvalue is going to be k, and we refer to this eigenvalue as the trivial eigenvalue, and all other eigenvalues are basically lying between -k to k. Okay, so we are interested in isoparametric constant. And due to this result by Alon, Milliman, Dodizuk, and Mohar, we know that isoparametric constant is bounded from the top and the bottom in terms of eigenvalues of the graph. So it says that let gamma be a k-regular connected graph with second largest eigenvalue is lambda 2, then it's lower bounded by k minus lambda 2 and upper bounded by this square root of this. Okay, so this k minus lambda 2 we refer to as spectral gap. So instead of studying isoparametric constant, we can study the spectral gap, okay, due to this result. And that's where we define spectral expanders. So what is it? It is an infinite family of k-regular finite graphs, like we defined, like we started with expanders, which satisfies the following two properties, which are if there exists some constant c prime, which just depends on k, such that spectral gap of each of the graphs in this family is lower bounded by c prime. And as earlier, the size of vertex set goes to infinity as n goes to infinity. Okay, so with respect to this picture, we are basically, this is the largest eigenvalue, always k, this is second largest eigenvalue, and spectral gap is c prime. So we want that spectral gap to be lower bounded by c prime. Okay, so better this the more the c prime is, better the spectral expanders is. Okay, but can we do arbitrarily large this spectral gap? We cannot, due to this result by Alon and Bopana, which says that if we have family of k-regular connected graphs such that size of vertices goes to infinity, then in a long run, your second largest eigenvalue is always greater than or equal to 2 square root of k minus 1. Okay, so we cannot arbitrarily improve the spectral gap. Okay, so that's where we define these families of graphs called Ramanujan graphs. So what is it? It is a graph, okay, regular connected graph, such that its second largest eigenvalue is at most 2 square root of k minus 1. Okay, so if this is the first eigenvalue and this is 2 square root of k minus 1, all of its other eigenvalues are less than or equal to this. Okay, so again, we are desired to build expanders in terms of spectral gap, but we cannot arbitrarily increase the spectral gap, but best we can do is up to this point. So Ramanujan graph in that sense is best possible expanders. Okay, and remember, expanders are graphs which are sparse and highly connected at the same time. Okay, there are some non-constructions of Ramanujan graphs. This famous paper by Lubowski, Phillips, and Sarnak, and independently by Margulis, they constructed infinite families of p+1 regular graphs, p+1, I should say Ramanujan graphs, where p is a prime. Okay, and later on, Morgenstern in 1994 extended their constructions to prime powers. So prime powers +1, we have constructions of Ramanujan graph. For all other values of k, we do not have constructions of k regular Ramanujan graphs. Okay, in a recent breakthrough paper by Marcus Pillman and Srivastava in 2015, they showed the existence of infinite families of bipartite Ramanujan graphs for any degree greater than 2. Okay, so these are some existence result and non-constructions of Ramanujan graphs. So that's basically the motivation for us about the Ramanujan graphs. Now I will talk about the graph under consideration, which is DKQ graph. It's denoted by DKQ. So it was introduced by Lazebnik and Ustimenko in 1995. So what is it? So we start with Q being a prime power, and let k be some integer greater than or equal to 2. So what we do is we construct two copies of FQK, so tuples of length k, such that each entry is coming from FQ. And we build the vertex set as P union L. So we basically take two copies of QK. One of them we refer as P, another one we refer as L. So P is basically, we'll think of them as points, and L we think of them as lines. Okay, so what is the adjacency relation between any two? So if I pick some point from here, and if I pick some line from here, and points are with parentheses and lines are denoted with square brackets. So what is it? So it's a tuple P1, P2, P3 up to Pk, where Pi's are of course coming from Fq, L1, L2, L3, Lj up to Lk, where Li's are coming from Fq. These two tuples are going to be adjacent if and only if this satisfies this system of equations. Okay, so we have k minus 1 equations over here. What are those equations? First is if P2 plus L2 is equal to P1 L1, and all of this equality means in the field FQ, finite field. Okay, P3 plus L3 is equal to P1 times L2, and when j is greater than or equal to 4, we have this relation. If j is 0 or 1 modulo 4, then we have Pj plus Lj is this. If j is 2 or 3 modulo 4, we have this equation. So this is basically the definitions of this graph called DKQ. Any question about the definition before I proceed? Okay, so let me give you one example so that we are good with the definition. Let's take Q be 2 and let's take K be 2 as well. Then we take P and L as F22, and gonna be vertex set is gonna be P union L. So basically they are tuples of length 2. So they're gonna be 0, 0, 0, 1, 1, 0, 1, 1, and similarly for lines. So let me take 2 of them. So let's take this and this. So 1, 0 is adjacent to 0, 0, because if we add 0 plus 0, it's gonna be 1 times 0. Okay, and similarly for all the edges, you can check this equation and it's gonna satisfy for all of this. Okay, so that's one example of these graphs, DKQ. Some properties of graphs, DKQ. These graphs has been well studied. Lots of structural properties and other algebraic properties of these graphs has been studied. So starting with the basic ones, these graphs are Q regular. Why they are Q regular? So if we start with P1, P2 up to Pk, and if I take L1 to be any point from FQ, basically by the equations, those k minus 1 equations I had, I can determine L2, I can determine L3 dot 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 Lk. So all of those I can determine if I start with some L1. So I vary the L1s and there are few choices for that. And that basically means that these graphs are Q regular. Sure, they are bipartite and number of vertices are QK plus QK. So that's going to be 2QK. Okay, so these graphs are regular, bipartite, and that many words. In 1995, Lazebnik, Ustimenko, and Voldar showed that DKQ are not connected whenever k is greater than or equal to 6. And they showed that their number of components, connected components, are basically q to the power j, where j is filling a 1 plus the fraction k minus 5 divided by 4. Okay, so starting with 6, we have 1 plus 6 minus 5 divided by 4. That gives me 2. That gives me 2 from here. So we have, I think this is supposed to be floor. Yeah, so we get 1 out of here. Yeah, and that's where we will get some floor or ceiling over here, and we have that many isomorphic connected components in these graphs, and each of them are isomorphic to each other. So a connected component, we will denote it by CDKQ. So we can basically study one component because all of them are isomorphic to each other. But one of the main importance of these graphs, and that's what the motivation to define these graphs, coming from this thing that girth, that is the length of the shortest cycle in this graph, is at least k plus 4 when k is even, and at least k plus 5 when k is odd. So basically what we have is the graphs, bipartite graphs, that gives us the best known general lower bound on this quantity, which is if we fix number of vertices, maximum number of edges in a graph, such that we avoid these cycles of length 2k plus 1 up to c3. Okay, so that's why these graphs has their own importance in extremal graph theory, and the lower bound then they provide is basically this: n to the power 1 plus 2 divided by 3k minus 3 plus epsilon, where epsilon is 1 if k is even and it's 0 if it is odd. Okay, none of the construction has beaten this bound so far. So this bound is the best known, and it's attained by this graph. Okay, and there are other properties of this graph has been studied as well. For example, automorphism growth, and whether this lower bound is attained, tight or not, like that. Okay, but what we are interested in is this conjectured by Ustimenko, which is about the spectral properties of this graph. So conjecture says that second largest eigenvalue of a connected component of DKQ is at most 2 square root of Q. Okay, so remember, for a Ramanujan graph, Ramanujan Q regular graph, we say that lambda 2 is at most 2 square root of Q minus 1. Okay, so that basically means that if we able to prove this conjecture, we have constructions of almost Ramanujan graphs. Okay, so that's why this has the importance on its own, this conjecture, and there has been some progress on this conjecture. So this has been proved for k is equal to 2 and 3, and for all values of k, by Lee, Lu, and Wong in 2009, by Choba, Lazebnik, and Lee in 2014. Choba, Lazebnik, and Lee studied the spectrum of other graphs called Vanguard graphs, and for k is equal to 2 and 3, DKQ are their special cases. Okay. In 2017, Moorhouse, Soon, and Wilford proved it for k is equal to 4 and all values of k. Okay, and I'm going to talk about the result which me and Taranchuk proved for k is equal to 5, and that also implies k is equal to 6, and all odd q, that is prime powers where prime is odd. Okay, so let me briefly tell you what is the idea behind the proofs of these 3 cases. So what we do is basically we have a bipartite graph. Instead of studying this bipartite graph gamma, we study its distance to graph. So basically, if I consider 2 points, and if there is some, let's say P1, P2, and let's say P and R, and if there is some line L such that P and R, both of them are adjacent to L, then what we will have is P and R adjacent in this component. Okay, so this pink one, it's called point collinearity graph. So basically it checks whether 2 points are collinear or not in the sense of points and line systems. So in terms of spectrum, we can study spectrum of either one of them, and it gives us the way to study the spectrum of the original graph. Now, since we are not studying the graph gamma itself, we are studying the distance to graph, which is point collinearity graph. The reason being is the point collinearity graph is a Cayley graph. Okay? And once we have a Cayley graph, we can study the representation of that by using representation theory. So there is some way to find the spectrum of these graphs, and then somehow we can show that the second largest eigenvalue is at most 2 square root of q. In all these papers, the idea is basically this, through representation theory of finite groups. For k is equal to 2, 3, and all q, the group, underlying group, is gonna be abelian. For these two cases, it's gonna be non-abelian. So now I'm gonna talk about some background on Cayley graphs and representation theory before going into the proof of our result. Okay. So again, our aim is to prove this conjecture. We can prove it for k is equal to 5 and 6 and all odd q. What we are going to use is representation theory of finite groups. Okay, so let me define Cayley graph. So we start with the group G, and let S be a non-empty finite subset of G such that S is equal to S inverse. What basically it means that if X is in S, then X inverse is also in S. And let's say one is not in S, that is identity of group is not in this set S, then take Cayley graph, which is denoted by this, is the graph whose vertex set is the group elements, and two group elements are adjacent to each other if there exists some element in S such that Y is equal to X. Okay, so this Cayley graph is basically size of S regular. And if it is connected if and only if S generates the group G. Okay, let's look at few examples. So let's take the group BZ6, that is strictly group of order 6, and let's take S to be 1 and -1. So 2, if I look at 2, and if I look at 2 plus 1, it's going to be 3. So we see that 2 and 3 are adjacent. If we look at 2 minus 1, we have 1, and we see that they are adjacent as well. Similarly, if I take the generating set as 2 minus 2 and 3, and if I look at 2 here, 2 plus 2 is 4, it's adjacent. 2 minus 2 is 0, it's adjacent. 2 plus 3, it's 5, it's adjacent. Okay, so that's Cayley graph. Now, once we have Cayley graph, we can use representation theory to study its spectrum. So let me talk about some basic definitions of representations. So what is it? So I start with the finite group G. What is a representation? A representation G is basically a group homomorphism from G to GLV. Okay, so where V is a finite dimensional vector space over C, and GLV is the set of all invertible linear transformations. Okay, so that's what representation is. It's group homomorphism from G to GLV, where V is a finite dimensional vector space. Now, what's the degree of this representation? Degree of representation is basically the dimension of this vector space over C, and it will be denoted by D sub rho. Okay, so representation, group homomorphism, whatever be the dimension of this V is the degree of this representation. Okay, now when can we say that two representations are equivalent? So we'll say that two representations are equivalent if we have some isomorphism, that is some invertible linear transformation from V to W such that sigma of G is basically T sigma G T inverse. And that has to be true for all G. Okay. So if we have such a linear transformation, invertible linear transformation, then we say that basically two representations are equivalent to each other. Okay, so representation, it's degree, and then we say that when two representations are equivalent. Now, due to this definitions, it's fine. We can study representation as a group homomorphism from G to G, L, and C. Okay, so what is G, L, and C? It's N cross N invertible matrices. okay, by change of basis and by this definition that they are equal. Okay? So sometimes we can study representation by this, and sometimes we can also study it like give the definition of representation in terms of invertible matrices. Now that's representations. Let me give you some examples. So let G be any finite group. We always have this representation called trivial representation. What does it do? It just basically takes G to 1. Okay. So C star is C minus 0. So you can check that it's homomorphism. All we need to check is rho G H is rho G rho H. That is the definition of group homomorphism. Okay. And given any group, this representation is always there. Another representation which is always there is regular representation, which is basically of degree the same as the size of the group. So what does it do? It takes a group element G to matrix RG. So matrix RG is basically a permutation matrix. That means each row and each column has exactly one non-zero entry, which is 1, and the entry is if y is equal to xt, okay, and 0 otherwise. So if I draw it, and if x is here, y is here, there is gonna be 1 at this entry if y is equal to xt, otherwise 0 everywhere. Okay, and again, one can check that lambda regular representation is a group homomorphism, and that implies that it's a representation. Okay. Now, representation, degree of representation, and some examples. After that, I'm going to talk about irreducible representation. What is it? Let's start with some representation rho. A subspace of W or subspace W of B is called G invariant if I take any G from G and any element W, then rho G of W is going to be B. So what is it? If I have some group G and this is V, this is P, this some W such that if I pick any element G from here, so I have rho of G, and it takes element rho, it takes element small w to in this set only, and it has to be true for all elements here. Okay, that's what G invariant subspace. Now, what is irreducible representation? An irreducible representation basically is the representation whose invariant subspaces are just the trivial ones, just either the 0 or the full one. Okay, that basically means that irreducible representations are those which do not have sub-representation. Okay. Now, if we have two representations, rho 1, W1, rho 2, W2, we can construct another representation by taking the vector space as direct sum of these vector space. And this new representation is just called the direct sum. What it does is, if V is W1 plus W2, on W1, it acts like rho 1, on W2, it acts like rho 2. Okay, so that is direct sum of two representations. So irreducible representation and the direct sum of two representation. That's what I introduced. Now, this famous theorem in the representation theory says that every representation of a group G is the direct sum of a finite number of irreducible representations. So it's like basically every number can be written as a product of prime numbers. So if we are studying representations, somehow we just need to study irreducible representation, because every other representation is a direct sum of irreducible representation. Okay. And we denote the set of all irreducible inequivalent representation by G hat. It's called dual of G. Okay. So G hat, set of all irreducible pairwise non-equivalent representations of G. Now, given a group G, we are just interested in all irreducible representation, non-equivalent ones. And there is another theorem which says that if I have this regular representation, remember I introduced this regular representations, then this regular representation basically a direct sum of all the irreducible representation ones. And each of them just repeats as many times as the degree of that. So D row 1 is basically means that row 1 direct sum row 1, direct sum row 1, row 1, and this is just D row 1 number of times. And same goes for other. Okay. So again, regular representation, we can write it as a direct sum of these. That also means because the degree of regular representation is same as the order of group, it's basically gonna be sum of squares of these degrees. Okay, so that's what we have this result. This is gonna be useful when we are interested in the spectrum of Cayley graph. Okay, so remember Cayley graph, what is it? It's defined by this definition. And if we are interested in the adjacency matrix of the Cayley graph, it's just gonna be summation over all the elements of the generating set of this RS. Okay, because when do we have two elements X and Y are adjacent? If we can, so there is one here, if we can write Y as XS. Okay, and how many number of times we have one in each row? As many elements as we have in the generating set. So if we take just the RS, it's going to be the summation of all these matrices. And due to the previous result, we know that this regular representation is equivalent to the direct sum of these irreducible representations, which means that we have some matrix which makes all these elements, this RSs, similar to this block matrices. Okay, that means what we can do is we are interested in studying the spectrum of this big adjacency matrix, but instead this big adjacency matrix is similar to some matrix, some block matrix, whose blocks are coming from this regular representations, which are these. Okay, so I'll say it again. I some group G. Let's say I have all its irreducible representation G hat, and for each irreducible representation, what I'm gonna do is I'm gonna define this matrix rho IS, capital S, which is basically the summations over all the elements of the generating set of this rho IS. Okay, so this theorem which says that if I have adjacency matrix of the Cayley graph, then its characteristic polynomial is basically the product of characteristic polynomial of these blocks matrices. That is this one. And this power D rho I just means that each block is repeating D rho I times. Okay. So for Cayley graphs, I have a big matrix. I want to compute its spectrum, but instead I have such smaller matrices, ideally, and I can compute the spectrum of those smaller matrices, and I will get the spectrum of the big one. Okay, and all this just follows from this important result, which says that if I have a finite group, then its regular representation is equivalent to the direct sum of all irreducible representation, and each of them repeats D rho I times. So yeah, perhaps I should take a pause and ask if there's any question. All right, then. So that was the background for Cayley graphs and its spectrum. So remember Ustimenko's conjecture. What does it say? It says that if I start with any prime power, then second largest eigenvalue of a connected component CDKQ is at most 2 square root of Q. Okay, so in general, DKQ are not connected, but each of its components are isomorphic to each other. So I'm just going to talk about one of it, which is CDKQ. Okay, and our result says that if I have a prime, odd prime, and if I take any power of it, then second largest eigenvalue of D5Q is at most 2 square root of Q. Okay, so D5Q is connected. So it's fine if I talk about D5Q or CD5Q. Okay, so these DKQ graphs get disconnected when K is greater than or equal to 6. So now I'm gonna give you the sketch of the proof. So it is divided into few lemmas. So first lemma is basically this, which says that this graph D5Q is basically adjacent to another graph, which I call as gamma 5Q. Okay, so let Q be an odd prime power. And again, I just take two sets, P and L, which is FQ5. And I take what is as P union L. Then D5Q is isomorphic to gamma 5Q. What is gamma 5Q? Similar to the like D5Q, we take vertices and then two tuples of length 5 are adjacent if they satisfy these four equations. Okay, that is P2 plus L2 is P1 L1 and so on. But in D5Q, those system of equations were these. So the benefit of writing in another system of equation is that notice that on right hand side we just have P1 and L1, but on the right hand side for D5Q we have P1, L1, P1 and L2 we have, then we have P2 as well, we have P3 as well. Okay, so instead of just working with D5Q, we can work with gamma 5Q, whose system of equations are now these. So again, two tuples are adjacent if they satisfy these four equations. And all these four equations are over finite field Fq. Okay, the proof is not so difficult. We just need to give one isomorphism between them. And over here, that isomorphism depends on something where we divide by 2. So that's why we have to choose Q to be in odd prime power. Because if it was even, then characteristic of that field is 2 and we cannot divide by 2. All right, so again, my aim is to prove that second largest eigenvalue of D5Q is at most 2 square root of Q. Now, instead of D5Q, I work with gamma 5Q. Now, second lemma I'm gonna say is that point graph of the gamma 5Q is a Cayley graph. So for Cayley graph, I need to give you a group and a generating set. So what is going to be the group? Group is basically this. So underlying elements are basically FQ5. So tuples of length 5, where alphabets are coming from FQ. But operation, the binary operation is like this. So X dot Y is gonna be this. Okay, so X, I'm just writing for X1, X2, X3, X4, X5, and Y I'm writing as Y1, Y2, Y3, Y4, and Y5. Okay, so what it does, X dot Y, it adds the first coordinate as it is, like addition is over FQ, X2, Y2 as it is, X3, Y3 as it is. But for the last two coordinates, X4, Y4, what it does is X4, Y4 plus 2, X1, Y2. And for the last one, it does is X5 plus 5, Y5 plus 2, X1, Y3. Okay, so that actually makes it non-abelian group. Okay, So this is the group I'm gonna be talking. And now for a subset S, I'll just take these kind of tuples, x, xa, xa square, x square a, x square a square, where a and x are elements of fq such that x is non-zero. Okay, so notice that size of this subset is q times q minus 1. So I'm working with this graph gamma 5 fq. I give you the group, I give you the subset. Now next lemma says basically that the point graph of gamma 5q is isomorphic to the Cayley graph whose group is this and whose generating set is this. Okay, so again, remember gamma 5q is basically bipartite graph where one part is referred as points, another is referred as lines. And I'm just talking about the point graph. That means two of them are adjacent if they are collinear. I'm saying that this point graph is basically isomorphic to a Cayley graph whose group is this and generating set is this. So proof just follows by system of equations. So 2 points, let's say P and let's say R, has to be adjacent in this graph if there is some line, I should write it as square brackets, such that both of them are adjacent to each other. And if I look back the equations, this has to satisfy this one and this one. And if I subtract from each other, I'm gonna get this system of equations. P2 minus R2 is P1 minus R1, L1, L1 square, P1 square, R1 square, L1, and so on. Okay. Now one can check, it's a little bit of work, that this is actually true. All we need to say that X is P1 and R1 and A is basically L1. Okay, so 2 points are adjacent and one can say that the first coordinate has to be not same. So that's why P1 minus R1 is non-zero. So X is non-zero and A is L1. Okay, so just write the definition of this Cayley graph and see that these are satisfying the system of equations. So yeah, first lemma, I can work with gamma 5q. Second lemma, I can work with this Cayley graph. So G is this and S is this. And remember, now we have a Cayley graph, we can use the representation theory. Okay, but before that, I'm going to give you the third lemma, which says that how can we go from the spectrum of the point graph to the spectrum of the original graph, original bipartite graph. So this lemma basically says that every eigenvalue lambda of the point graph with multiplicity m corresponds to a pair of eigenvalues, that is plus minus square root of lambda plus q of the graph gamma 5q. Okay, so if I find the spectrum of point graph, I can find the spectrum of the original graph. This just follows by counting the walks of length 2 and with the observation that gamma 5q do not contain a cycle of length 4. Okay, and then we just write the adjacency matrix, square of that, and adjacency matrix of the point graph. So that means what? That means Ustimenko's conjectures ask us to prove that second largest eigenvalue of CDKQ is at most 2 square root of Q. And what we now have to show that second largest eigenvalues of the point graph, which is Cayley, is at most 3Q, because 3Q plus Q is gonna give us 4Q, and that is 2 square root of Q. Okay. So Cayley graph, whose second largest eigenvalue we want to show is at most 3Q. That's what we have so far. Now, coming back to the representation and technical part. So we have group G, whose operation is written here. There are basically 3 different types of irreducible representations. So I know that there's a lot of notations. So first irreducible representation, I call it as type 1. So what is it? It's basically if I take alpha, beta, and gamma, 3 numbers over FQ, then it's defined like this. So it's zeta to the power trace of this alpha x1 plus beta x2 plus gamma x3. So what is zeta? Zeta is e to the power 2 pi I divided by p, that is primitive pth root of unity. And what is a trace function? Trace function is from fq to fp. So I'm assuming here that q is p to the power e. So what it does, it takes the element from fq a, element a to a. Oh boy, sorry about that. Yeah. Okay, so it takes the element a to a plus a to the power p plus dot 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 a to the power pe minus 1. So that is type 1 representation, and this 1 indicates that degree of this is basically 1. Okay, and alpha, beta, gamma is over fq. So how many of them do we have? We have q cube number of representations of type 1. Second representation of type 2 is basically this. So degree of this representation is q. So that means I'm going to give you the representation as in q cross q matrix. So what it does, it's a matrix whose jkth entry, so it's indexed by fq, whose jkth entry is given by this. So again, zeta, primitive root, then to the power trace of this summation. Okay, and this delta basically means Kronecker delta. So if 2x1 alpha plus j is equal to k, then we have this entry, otherwise we have 0. So it's kind of permutation matrix. Each row and each column has exactly one non-zero entry, and that non-zero entry is given by this expression. Okay, this complex number. So how many do we have? Alpha, beta, gamma, where I want alpha to be non-zero because I'm dividing somewhere by alpha. So number of these type is q squared times q minus 1, and they are of total degree q. Similarly, we have third type, tau and mu over fq. I want tau to be non-zero. So how many of this type? Q times q minus 1. And this is also of degree q. Okay. So this is q cross q matrix whose expression is given like this. So these are 3 types of irreducible representation of this group. And we can check that sum of squares of the degree is same as q to the power 5. And by using the character theory, we can show that these are actually non-equivalent. Okay, so I cannot go into the details like how they are representation and all, because it's get very technical easily. So we have group, we have representations. Now we want to compute the eigenvalues coming from these representations. Remember, the generating set is given like this. So all we do is just add chi alpha beta x, where x is coming from S. That means we are adding this expression. This is of degree 1, so that means 1 cross 1 matrix. So whatever this summation is, it's gonna give you the eigenvalues directly. Those eigenvalues are basically distinct ones. They have some multiplicities, of course. So those are q times q minus 1, q, 0, and minus q. Okay, and this is basically the trivial one. And we want to show that non-trivial ones are at most 3q, and that's exactly true in this case. From type 2 and type 3, it's very technical. So I'll just give you some idea what it is. So what we do is we write the summations of these matrices, which is the summation of these matrices. So what we do is we find the explicit expression of jkth entry of this summation. After that, what we can show is the eigenvectors of these 2 matrices are coming from multiplicative characters of finite field, And once we have that, we can find the expression for eigenvalues of these matrices. And those eigenvalues are basically sums which involves multiplicative and additive character of FQ. So we do not have explicitly know what is the eigenvalue. What we have is expression of each of the eigenvalues, which is basically the sum of characters of FQ. But luckily, this famous bounds that is known as Wild's bound, it gives us a way to bound the absolute values of those expressions. And by using that Wild's bound, we can show that there are at most 3Q. Or okay. Yeah, due to the time constraint, I cannot go into the details. So that's how this follows. So my last slide, just to summarize. So we are interested in this conjecture, Ustimenko's conjecture. What is the importance of this conjecture? The importance of this conjecture that it says that DKQ are almost Ramanujan graphs, and we desire to build Ramanujan graphs. So that's the importance of this conjecture. And what we proved is if Q is an odd prime, then second largest eigenvalue is at most 2 square root of Q. That is, we proved the smallest open case, that is K is equal to 5, and we could prove only for Q being odd prime power. And as a corollary of this result, we proved that it is true for K is equal to 6 as well. Why? Because D6Q is basically Q isomorphic copies of D5Q. So each CD6Q is nothing but D5Q. Okay, so if we have the result for D5Q, we have the result for K is equal to 6. Okay, and for future work, we want to prove this conjecture for other values of K. So smallest open case in that case is K is equal to 7. Yeah, maybe by using representation theory or maybe by using other techniques. Yeah. Yeah, so the paper is archived. We archived in July last year, and it's under peer review. If you are interested, you can look into it and feel free to email me. So I stop here. Thank you for your attention.
Thank you for talk. So is there any question for our speaker?
Can you say briefly the what makes it hard for higher values of K?
Yeah, so in this case, representations are of degree 1 and other are degree Q. We tried for D7Q. It seems that irreducible representation of degree Q square. So computing the eigenvalues of those are getting difficult. So, and we suspect that as K grows, the degree of representation is also growing.
But so you can understand the representations, but then you can't bound the eigenvalue, or you can't even understand all of the representations?
We can't even understand the representation, but by using some theory, we can say that degree grows.
Okay, I understand. Thanks.
I have a quick question. So does it happen the same thing, like, because that, like in this group that you have, the generating set is like this alternating powers, like x, ax, ax square, and so on?
Right.
So you get something like that when you have higher case? Because I mean, you need this isomorphism to move you from those PJs to move everything in terms of P1 and L1. That's
right. So for K is equal to 5, we can write the equation in terms of P1 and L1. But if we increase the K, we cannot even write in terms of P1 and L1.
okay.
So,
okay.
Yeah.
So it's difficult. Yeah. The other question I had is like, what would be, because in order to do like this, because we talked about it, if you want to do this infinite family of expanders, you want to turn it around the other way. Look at the D3K, like fix the fix the, well, no, DK3, fix the Q and
Right.
move the K.
Right. Yeah, no idea about that. How can we do that? Yeah, but like, yeah, if we need family of expander, we need to fix the K, and then we need to fix the Q and vary the K. Yeah.
So do you know like any results for like different forms of these graphs DKQ? Let's say for if you have like a larger K, to give you a graph that's isomorphic to it, but in which the right hand side maybe has fewer, you know, the indices don't go all the way up. Maybe there are fewer.
We have some partial result for that, like let's up to 3/4 of number of variables.
Okay, but it's still like that could be quite large. Yeah.
Yeah.
Okay. Thank you. Very nice talk, Himanshu. Good job.
Thank you.
Is there any other questions?
Maybe I'll ask one. So wild speculation. Do we know any examples where we can take a graph and add a matching without changing the second largest eigenvalue?
Add a matching without.
I mean, if you can increase the degree here without changing the second largest eigenvalue, it's wild speculation. But I wonder if anyone knows if you can add a matching to a graph without distorting the second largest eigenvalue. You need those eigenvectors all to sum to 0 on that matching, I guess.
I am not aware about that. If anyone else is.
Yeah, it's just a crazy question. Sorry.
So any other questions?
I have one. Yeah. Thanks, Himanshu. I was wondering if you could say anything, or if you know anything about the relationship between the group that you're using to build your Cayley graph for the point graph in this case, and is there a relationship with the groups in the previous papers, like the Williford, Sun, Morehouse paper? Like
Right. So it's basically yeah. So if we just look at the first 4 coordinates, that's what exactly it is. Yeah.
Okay, that's exact. Okay, so it's definitely okay.
Yeah, and like for k is equal to 3, if we just look at the first 3 coordinates, and k is equal to 2, just 2 coordinates, and that's why k is equal to 2 and 3, it's abelian. And
right.
Yeah,
got it. Okay, so yeah, thank you. Very clear answer to my question. Thank you.